Making a video. Draft science. So generally on the subject of conservative force, maybe. Specifically more about gravity than anything else. Maybe kind of gravity waves a little, I don't know. See where it goes. Curious facts. Okay, so you have these two kinds of things in the universe in terms of you got like suns, and then you have things like galaxies and solar systems, which are, so you have these things that are basically round, and then you got things that are basically flat. Interesting. Something worth accounting for. So just so many things I was thinking about, and it's just tying things together. So how do I want to approach this? So anyway, that's a curious fact. And so you have this idea of conservation, which is this whole gravity thing. So, if something goes in, it has to come out. It's the way it works. There's no, unless it stays. Unless you absorb it as mass. You either change the mass in the system, or you have to, whatever energy goes in has to leave somewhere. It has to be accounted for. So by my theory, it doesn't really matter if the universe is actually balanced, in the sense that if the whole universe was moving 100 miles an hour that way, probably wouldn't be able to tell. Maybe if it was going a lot faster going that way, you would, because everything would get a little misshapen. I think our solar system's a little bit out of shape. I mean, I think there's, it tends to be, all the planets tend to have their ellipses and similar, if not, not really similar, but there tends to be more on one side than there is on the other. More time is spent on one side of the solar system by the planets than is spent on the other side of the solar system by the planets, kind of a thing, which would indicate it's either moving that way or it's moving that way. I tend to argue it's moving in the way the little things are going, and the big thing is dragging along. But clearly the sun is moving in the galaxy, the Milky Way. So clearly the whole solar system is moving. And that has to be accounted for. So this even gets back to the, it goes even to the argument I was making about velocity. And, people argue that I'm arguing for a very intuitive perspective. But in a way, what I'm arguing is it's very unintuitive to think about velocity and think about momentum and think about the energy involved of like a bullet hitting an apple or something. And thinking in terms of not so much that the bullet might fragment because of something about the energy of the impact, and that the real thing that's happening is that the velocity has degraded the matter of the thing moving, and that degrade of its character, of its integrity, has made it possible for it to spread and it's weakened it and made it blend into the apple in a way, to eat the apple, to have apple go into it, because it doesn't have the same integrity. Where if I push a bullet with my finger into an apple, the bullet's not gonna blend with the apple at all. And so it's a very unintuitive way of seeing impacts, as not so much about the fact that something's moving and that means it has power. It's that the fact that it's moving means that it has weakness. It's like completely opposite. So anyway, the universe is this balance thing, right? I'm arguing that there's these bits, and they all have as many going this way as there are that way, this way, this way. So we have to always account for them. You can't produce some going that way without having explained where you, if you If you create an imbalance somewhere, there has to be the opposite imbalance somewhere else. That's the conservation element of force. And this is true for everything. You know, magnetism, electricity, all these forces are conservative forces. So part of what I was thinking about is that the velocity is essentially creating charge. See, they have this idea. The idea is that you can create charge with friction, you know, by rubbing things. And it's not the rubbing, it's the velocity, the movement of all the pieces that is really creating the charge. That velocity is what's expelling, converting a bunch of this quanta, and through that process you've changed the dimension of the three: forward, up, left, right, up, down, and that's that change in movement from one dimension to another dimension releases this stuff going in the perpendicular direction and out the side, so to speak, of your velocity, and that's what creates charge. So essentially, if a bullet is moving fast through the air, that it's essentially creating charge coming out of the sides. And hard to measure, obviously, of a moving bullet, but that's actually what creates all that, you know, the pressure wave thingy, the idea of the turbulence and all this other stuff. That's not so much the intuitive response, oh, there's friction and there's this and there's that. No, what there is this the consequence of this is the release of this, you know, stuff coming out perpendicular. So I was thinking about gravity in those terms and why galaxies are flat. And, you know, a simple explanation, or an explanation is, well, yeah, you have a bunch of things orbiting and they're going to tend to bend each other into a straight line through gravity, through attraction. You know, the planets would just tend to rock their ways into a flatness. But it could be that what's really happening is the energy, the pulling, the attraction is creating a repulsion in another direction out the top, so to speak, and the bottom of the galaxies, our solar systems. And that there's actually, this might be the explanation for the dark energy, the repulsive force that exists in the universe, is the fact that, yes, for this, the consequence of this attraction is this repulsion coming out of the top and bottom, the sides, the perpendiculars. So it seems an interesting, I mean, something to play with in terms of figuring out the conservation that takes place in these interactions. And, you know, the difference between the sun and the galaxy, just to get to the punchline of that question, I suppose. My short answer, short meaning short thought on the subject, is that the difference is just in the condensation. So the more condensed the matter, the more obligatory the spherical shape, and the more spread out, that obligation is lost, and you're expelling your dark energy in fewer directions. And there is a tendency for things to squish a little. I mean, the Earth is fatter than it is tall. You know, and they blame that on centrifugal, but there could be more to that story. But anyway, let me, you know, so there could be a tendency to things, you know, but like I say, it's like as you push it closer and closer together, it just can't, it wants to spread out, but it can't because of the gravity, ironically. And so it's a forced issue. It's the way it looks by force, not the way it looks like by what it would look like if these other forces weren't involved. The trade-offs, or whatever you want to call them. Alright, so what really got me to this is just, you know, further contemplation on the idea of how this gravity thing, how it works, and the fact that you do have to have this conservation. And so, in the response to Hofladay, I went a little bit into velocity and the idea that when you're going forward, or you have a velocity this way, you're changing the identity of what you possess. So, to make a simple, to draw that simply, would be that your matter goes from this, something balanced, to something unbalanced, in the sense that you have this extra in one direction. But technically, to have that extra and retain the same mass, you have to lose some of this other stuff, and to make the difference. And clearly, you could lose all of this if you're replacing it with the extra this that you're getting from the environment. So I mean, the consequence of having this is that you're moving into the field and you're experiencing more of this. So this can replace this. And you're trying to do the addition. But the tricky part are these tangents, these perpendicular dimensions. So the up and down and the, this way, that way thing. Those two dimensions, the X and the Z, let's call them, and we'll call this the Y or whatever, they still have to be moved with this thing you have, this velocity. Now, the consequence of you having this extra is that you're going to tend to go in that direction, spread across your entire mass. But those tangentials still have to be dealt with. They still have to, they have no interest in going this way. They have an interest in going this way and that way and that way, but they don't really have an interest in going that way. And so something has to happen to them for you to do this. So the idea is well, anyway, so let's just say this was the Earth and the Sun, and these aren't obviously not drawn to scale. But the idea is there's a constant acceleration, all right, of the Earth towards the Sun. I mean, constant, an unceasing acceleration. It doesn't gain any ground, but there's still always the same amount of acceleration, and it's constant towards the Sun. And that acceleration is basically an expression or consumption of this direction. So this direction is being consumed by this acceleration constantly to come up with this idea of what will eventually be this circular orbit. I mean, it will average out to this circle. So the one acceleration is killing a velocity in the other direction. So the velocity is constant, and this acceleration is constant. So they're really just two velocities in a way, but the acceleration is the important word, just because the acceleration is where you're actually doing this gaining of an arrow. So having two extra, having the imbalance of velocity, two extra arrows going in the direction of your velocity, let's say. Having it and obtaining it are two different things. Having it has a consequence, and obtaining it has a consequence. So you can sort of understand having it, okay, there's sort of a balance innate in that. We still haven't dealt with these perpendiculars when you have it, because obviously they're going to, here there's this idea, okay, you're moving in this direction, so you're gaining this, you can get rid of this, the opposite direction, because you're getting more opposites in the field. But you still have to blip out these tangents. So these, these tangents, you're going to lose them for some percentage of time. You release them. They won't in a sense exist, and we'll call that time dilation. And then you'll reestablish them in this new forward position. So you'll you'll wipe out these perpendiculars for some portion of time, say 1/10 of a second or whatever. Yeah, we could just say it. We could just make up a number. 1/10 of a second. These things don't exist, and what they really are going to be replaced by is this forward thing, this extra forward you have. And that's going to have to be maintained throughout your velocity. And so, even though you're going to be letting loose these things, and then you'll reabsorb a new one. You'll get rid of this one, and you'll regain a new one from the field somewhere else, which will essentially be, here you're going to be creating a push into the world, and then here you'll be, when you reabsorb the what you released, when you reabsorb it from down here, it's coming in, and you'll absorb it and keep it this time, then it's going to be a pull. So this is going to be what's going to be perceived as a pull, but you're going to be having it as a push, and later. So it'll even out in a sense when you have just regular velocity. But again, acceleration is different. So the idea is what gravity does is this acceleration is the absorption of the arrow, the directional identity, and this thing just keeps absorbing arrows going towards the sun, and so that's essentially creates the low pressure here. There's fewer of these arrows because the Earth has to convert the arrows it has into arrows going this way to do this accelerating towards the sun, and that creates what I describe as the shadow, the low pressure that stimulates or creates the counter response in the sun, in the sense that the absence of pressure coming this way means the field pressure from normal space pushes it a little bit in that direction, or again, see, push is the wrong word. Gravity is neither push nor pull in a sense, because it requires this absorption, but the fact that it's getting more coming from one way than it's coming from the other way just means it will naturally, by just its random function, absorb more. So if the wind is blowing, you will tend to move with the wind. But it's not happening like wind is, where it bangs off of you. It's happening where you are absorbing elements of the field in all directions. And if one element is heavier than another element, the other side, there's more wind on one side than the other, your identity will change to reflect that, and you'll move as the wind moves. You'll become the wind, so to speak. And that's sort of like what gaining velocity is. You kind of become part of that imbalance. You imbalance in symmetry with the field around you, which is a lot like electricity and all that stuff, but I don't want to get into that. So anyway, there's this. So the sun is absorbing more, but what it's doing, it is doing it on this plane of the dimension. So it's this entire dimension, it's accelerating. So it could be accelerating a little this way and this way. Anything that has substance in this plane is where it's going to express the absorption. So an arrow could be coming in this way, and it'll absorb it. So there'll be an absence of this arrow, so there'll be a low pressure in that direction, a low pressure in that direction. So that's why gravity ends up spreading. So it's this object out here. I mean, this just confuses things. Yeah, sorry. That is not a planet. So this absorption creates these vectors of absence or shadow that's spread out in this entire plane. So anything on this side, the same side as the thing causing the, that ate, to create a shadow, and this shadow, the shadows just always end up being anywhere in that direction, just as these arrows, the thing moving the earth towards the sun could be absorption of anything on the plane, okay, that's parallel to the sun. So anything moving, anything that would be going through, that would come out on this side at all, could be part of, a component of, what could be considered velocity towards the sun. And so they're really the energy is converted into the light bulb effect, the spreading of the gravitational low pressure. So even though it's something happening very directly between these two things, in that this accelerates, causes a lowness in the pressure, this accelerates back, causing more lowness, this accelerates back. So that's the induction part. But instead of being able to, they don't communicate through this like a laser beam of low pressure. They communicate that low pressure across the entire dimension in the absorption. And now the trick is what are they releasing? What's being let loose through this constant acceleration. So again, it's a constant acceleration of the earth towards the sun. And what it's obviously letting loose is everything in, obviously the thing being changed is this, okay, direction. This velocity is being lost. So it's obviously losing arrows going this way more than any other kind, because it's moving this way. But it also has to move those tangents. So again, it's back to this argument that part of, so I mean, you would say that, okay, the obvious thing, it would be, well, there should be a huge pushing force going this way. But what it's really doing is, instead of just disposing of it this way, it's replacing it. That's why the earth continues to move, is because it retains a big portion of that velocity. It's still, see, on the same plane, it's still the same direction in a sense. It's still moving in the same, in that same 180 degree thing. It's still moving in that 180 degree plane. And what it's really doing is getting rid of time of tangent. The other two, these two perpendicular dimensions actually are not existing more of the time. So they're the place where that's what you're actually disposing of, is the tangents. So if your velocity is this way towards the camera, I would be creating the low pressure being created between me and the camera would be compensated by a higher pressure going in the other two perpendicular directions. And by other two perpendicular directions, I mean that whole plane. And the two planes mix, as you can see. I mean, this plane will intersect in a sense with this plane. 45, well, at 90 degree angles. Which just makes the whole thing a little bit more complicated. So I guess I don't know if I want to even go there. Even this again, the drawing does turn into slop. So how do I still want to, yeah, I just want to get to that point that you always have to understand that these two other directions, the four other directions, when you have velocity, they have to be pushed along, and they really can't be, because the conservation thing, these you can never convert an arrow. You can only just exchange it. You can only exchange direction. You can't change direction. You can only exchange it. And so if if this has to move, then this can't be this. It has to be, for some period of time, converted into this. and this has to go out into the environment. So this has to be lost for some moment of time. It's just a small percent. I said 10%. It's just 1/1,000,000th of a second kind of thing at low velocities. But it's still, it's enough time, a 1/1,000,000th of a second, of a release of higher pressure. So what would be called dark energy would, I think, be reasonably described as a consequence of that. So anyway, what I'm theorizing would be the consequence of this, is that you could argue that this motion that happens in a solar system, so we have this acceleration happening where the planets are accelerating towards the sun, and that the consequence of that is likely that there is extra energy that comes out here. That's the conservation. That the in does create an out coming out of the top, the flat part. And that the sun itself would be radiating more energy out of its top. Now, you see this in some cosmological illustrations. Anyway, I don't know if they have actual images of stuff like this. You know, we have these jets that, you know, when the thing supernovas, it novas in this upward, you know, it splits top to bottom rather than blowing up sideways. And that might be part of an explanation for that. You know, is when you have all this, you have a hyper acceleration in this direction, you end up with you know, hyper creation of low pressure, the low pressure that pushes things together, that you end up creating super high pressure coming out of the top and the bottom. So that you could maybe argue that black holes would have that kind of a signature, that, you know, facing you this way versus facing you this way would be entirely different. They would, you know, be pulling from one side and pushing, you know, from the other. Yeah, so I think it does. I think it's. I think it can. I think it can be useful to explain things, but I think it's just as a way of understanding the complexity of the conservation. That it's, you know, you really do have to account for what it took to pull two things, something together, and that's the acceleration, the conversion. And then once they're pulled together, there's no more acceleration. That for every bit you pull in, you push something out. So you could argue that the sun, once stabilized, its parts are accelerating in both directions. It's pushing and pulling constantly. And that it really takes an imbalance from the environment to create what we feel as this external gravity. That it really wouldn't manifest as gravity unless you had mass around it. So you have to have the masses that feel the gravity for the gravity to exist. See, is that applicable to charge or electricity? So yeah, it's almost like arguing that there can't be a charge unless there's the counterbalance, the absence of the charge. The ground has to be somewhere, or effectively the charge doesn't exist. Its potential exists, but it doesn't exist. So the potential for the sun to have gravity would exist if the sun was just sitting by itself. But it really can't manifest gravity until something's accelerating towards it. Until something creates the shadow that it makes the counterforce out of, the gravity, the pull. Because once it's condensed, there's basically a balance. Once it's in a sphere, there's no imbalance. So the sphere is incapable, let's say, of expressing imbalance unless it's moving. Again, if the sphere is moving, then it's going to be doing that perpendicular dimension thing. The two dimensions perpendicular to, so I'm moving this way, the two dimensions perpendicular to my movement would still be accounting for my movement, because they'd still have to be some portion of time they're non-existent. So you see, the trick is that, but when you have velocity, that ends up being balanced, in that you have the initial extra release, and once you have the initial release, it doesn't add up to any future release. So it only happens while you're accelerating. So while you're accelerating, the perpendiculars expel more than you consume. So while you're accelerating, you expel more on the perpendiculars. But when you're maintaining a velocity, you already did the expulsion, and now you're just maintaining the 90%. It's like stepping on the accelerator and just leaving it at one place. I mean, once you've done the acceleration, the movement stops from the sides, because you already created the deficit. You don't have to recreate it. You can't recreate it without accelerating. So accelerating is where you're doing the conversion, and that's the part where you have to release the conservative opposite reaction. But you don't need an opposite reaction when you already have velocity, because you already expelled your opposite reaction. You already did your opposite reaction in acquiring the velocity. Yeah, that's a better way to say it. So it's only when you're accelerating that you're disposing of the perpendicular dimensions to some percentage, and clearly disposing of the opposite direction. You don't need that anymore. Yeah. But what percentages, I have to work, that's the part I have to work out. What percentage of what you're disposing is in the exact opposite direction, and what percentage is these tangents that require migration. There's a percentage of time dilation per measure of material velocity, and that is defining how much of the perpendicular dimensions have to be not existing, what percentage of time that is. And like I said, for say if you're going 50,000 miles a minute, it still would probably be a small percentage of total time, because it's always going to be relative to the speed of light. It's always going to be a percentage based on relative to the speed of light, because that's what the native speed of all the little bits is. Alright, so maybe I won't push this. It's a little camera test anyway. Yeah, I have to do this better. So, but I see why I'm going to do a little rewriting, and I wanted to get this right about the conservation created in gravity, and that it's like the movement of charge is work. If I have two charges, a positive and a negative, two plates next to each other, and I pull them apart, they have to do work, because they don't want to be pulled apart. There's a force against you, and you have to go against that force, and the byproduct is you end up with a higher voltage potential. So that's your benefit for the work cost of pushing them apart to a place where they resist being pushed to. And so the argument is when you move a planet towards the sun, it's work, and that there has to be some expression for that work, some equal but opposite reaction. Yeah. So I was thinking, like I said, in the context of the gravity waves, because they're saying this, this gravity goes out to the universe, and you're just saying, well, that's a force. And so whatever that force is, whether it's a pull or a push, there still has to be a pull or a push going somewhere else to compensate for that, whatever that is. Whatever the wave is, there has to be a compensation for it somewhere. Now, I suppose it could be built into itself in the sense that you could have a pull and then a push in the same wave, and that would be conservative. But that's something to, I have to think about that one. I mean, the whole idea of converting matter into gravity is, like I said, I don't know how that fits at all with relativity, and that sounds more like my theory than their theory. But anyway, yeah. So sorry. I mean, I was hoping this would. I was hoping through this video I would be able to, get a. I grasp it, but being able to explain it, it's a little tricky because it's complicated. Because you have to keep thinking in these 3 dimensions, but you have to understand that that's a simplification, and that this forward dimension is really all the vectors going this way, and that you're just adding the forward component. You're just ignoring the component in any other direction and just adding the forward component, and that's the definition of the force this direction. Yeah. So anyway, so it does get complicated. But essentially that's why gravity is, even though it's traveling at the speed of light, it's slow in in the sense that, especially like in galaxies, you'd say it's so slow that the object creating the gravity, the I accelerate towards you, but you don't feel it for 10 years. And then you accelerate towards me, and I don't feel it for 10 years. And I'm not even in the same position anymore. And there has to be an explanation for that. And the explanation is that all I have to do is be somewhere in the same plane of that forward dimension. I just have to be somewhere on this plane. I just have to not move behind you to get the byproduct of what I created. So the acceleration I created in you doesn't have to be felt by me here. I can feel it over there because you're producing it in that spectrum. So you're not, even though I kind of laser beamed you, when I hit you with the low pressure, you produce it as a cone of light in all directions in that one direction. And so I can feel the consequences of the gravity I create, even though I moved way over here. Yeah, that's what I'm trying to get to. And well, that's the inspiration for this. But like I said, it has all these other little elements where you start to think about what it is to have velocity, and that really has nothing to do with you moving. I mean, I'm not. It just has to do with how you're changing. And yes, you're getting closer to something, or you're going to interact with something, but the only thing that changes the interaction is the fact that your structure is so different. It's the change in the thing that makes the interaction so different between two things moving, like 2 cars going 50 miles an hour right into each other. What makes the interaction different is how the 2 cars have changed when they're going to interact, not the speed itself. And that's the really interesting part. Yeah, anyway, enough of a video. Try again. Just keep poking at it, see how we do. So, Hopefully I was supposed to make some video about some further quantum issues, but haven't seen it yet happen. So maybe he's not, I don't know. Anyway, Till next time.